So I just forgot to start recording, so let me just repeat. I showed the complex shifting, which is very similar to the shifting in time domain. You get this exponential term either on the left side or on the right side, depending on where the shifting is. And I just showed the final value theorem. Using the final value theorem, if you know the transform of a function, then without knowing the original function in time domain, you can calculate the final value of that original time domain function by taking this simple limit. So on this example, the final value is calculated as 10 over 7. And this means whatever our function is, we know that it approaches a limit value as t goes to infinity of 10 over 7. We don't know what happens to the function in the low time range, but we just know that at the limit it approaches this constant value. Okay, but there's this important note about the final value theorem. This the function should be analytic on imaginary axis. In fact, this s times f over s, f of s should be analytic on imaginary axis. So if you look at this function, you multiply this with s, and this s term here disappears, and we're left with this part. And it is analytic on imaginary axis, right? So there are several points where this function is not analytic. One of them is minus 1 over 3. Okay, this is the point, one point where it is not analytic, and there are two other points, and those are the points that correspond to the roots of this second order polynomial. And this function is not analytic, but it is analytic on imaginary axis. Okay, so if we had s squared here, then multiplying with s would cancel one of the s terms, and then we would have one s remaining here, and this s gives an pole at the origin, right? In that case, we wouldn't be able to use the final value theorem. And as an example to that, we can consider the sine function. Okay, we know that the transformation of sine omega t is equal to this function. If you try to use the final value theorem, you will get the following results. You take this limit, limit of f of s times s as s goes to 0. That will give you a value of 0, right? So this limit gives you a value of 0, which says that the function approaches 0 as t goes to infinity. In fact, it is not true, because this is an oscillating function, right? As t goes to infinity, this function still keeps oscillating. It doesn't approach a constant value. So apparently the final value theorem doesn't give the correct answer here, but you can find the reason why. If you look at this function, you know that there are 2 points where it is not analytic, and those 2 points are on the omega imaginary axis, right? So the singular points of this function are minus j omega plus j omega, which are both on the imaginary axis. So that's why the final value theorem cannot be used here. And then we talked about complex shifting. And then the real convolution property. So in this property, if you have two functions, let's say you have f1 and f2, and you know the transformations of these two functions as capital F1 and capital F2. This property says that taking the convolution of f1 and f2 in time domain, and I hope you know the convolution operation, right? The convolution is just defined through this integral. And sometimes you put a circle around this star here to represent the convolution operation. So the transformation of convolution of these two functions is equal to multiplication of the transformations of these functions. Okay? Another sign that shows Laplace transformation makes operations easy. So the convolution operation is a complex operation. So when you're convolving two functions, you have to take this integral. But in S domain, the corresponding operation is just multiplication. Okay, so you just simply multiply the transformations of those two functions. Okay, so this is the convolution property, and there are some examples here which you can look at later on. Now let me go back to this other file which I found on the internet today. There are some examples here, so you can take a look at these examples. In fact, I'm planning to give you a homework on these properties, and you can study this file, for example, and you can find many other files yourselves on the internet as exercise, and those will help you do the homework. So if you look at these examples, you can see that the transformation of such functions become very easy by using the properties. So for example, we already know that the transformation of sine function is given by this relation. If you need to take the transformation of this function, you have sine term multiplied by an exponential term. And if you remember, this was in the solution of the springless damper example. If you remember the solution of the springless damper problem to initial conditions, in the result we had such a function. So you don't need to take the integral, the Laplace transform integral using this function. Instead, you can just refer to the complex shifting property. So f of t here is the sine function. You have f of t multiplied by an exponential term. So this exponential term just causes the function in S domain to be shifted by an amount a, where a is this coefficient there. So by using that property, you can immediately say that this e to power at will shift my function by minus a. So you can simply take the f of s, and instead of s, insert s minus a, and that becomes the transformation. Okay, I told you before we started this Laplace transformation that we normally don't use these integrals. Instead, we use Laplace transform tables. Here you see an example. And by using the elements in the table and these properties I just explained, you can find transformations of more complex functions. So in this table you have 1. This is the unit step function. The transformation is 1 over s. If you have e to power at, in fact we calculated this, right? So this was in the file I prepared. Let me go up here a little bit. I think that was the second example I did last week. Okay, so we calculated the transformation of e to power minus at using the Laplace integral and found the result as 1 over s plus a. And we can obtain this result by using the complex shifting property, and let's do that now. Okay, so let's now find the transform of this using the properties. Okay, first let me tell you that this function is defined in the positive time range, and you can equivalently write as e to power minus at times u of t. Okay, by multiplying this with u of t, you make sure that the function is defined in the positive t range, and for negative t values, its value is 0. So these two are equal. And my f of and I know that the Laplace transform of one over s, and if I use the complex shifting property, the Laplace transform of now let's remember the complex shifting property. If I multiply the function with e to the power minus 80, this just shifts the function by amount plus positive a. So to the f of s plus a, and this is u of s 1 over s plus a. Okay, so by just using the properties, we calculated the transform of this. And previously, we obtained the same result using the definition, using the integral. So let's make sure that the result was the same. Okay, yeah, so the same result was obtained by taking the integral. Okay, so it just shows you that these definitions or these properties make calculation of Laplace transformations easy. Okay, so let's take a look at this other example we did previously. Okay, so the transformation of this function was calculated using Laplace integral, and the result was found as this. Now let's see how we can obtain the same result using Laplace transform properties. Okay, so I'm looking for the transform of this function. Okay. Okay, so let's see. First, I have a part, an interval where the value of function is constant. Okay, but this is only in the 0 to 2 interval. So I can write this function as follows. This is equal to unit step function, which is this function. Okay, and if I subtract from that function this red function, I will get this part, right? So I take u of t, and then from that subtract u of, so this red function is what? Minus u of t minus 2, right? So here's 2. Okay, so this part just gives me this part of the function. Okay, and then I have the second part of the function, which is just this ramp function that starts from t is equal to 2, and I can write that part as plus t minus 2 times u of t minus 2. Okay, so it is really difficult to write here. So my handwriting is not really that terrible, but and especially when the pen gets close to the edges, you cannot really use it very well. So anyway, so this part, t minus 2 times u t minus 2, and so maybe I should use color to make this easier to follow. So let me make this red, and that red part corresponds to this part of the function. And let me make this part blue. And that blue part corresponds to this part of the function. Okay, now let me calculate the transform of this function. Well, first of all, the linearity property tells me that I can take the transformation of these functions one at a time, right? So this is equal to Laplace transform of all these things. Is equal to the Laplace transform of the unit step function plus or minus the Laplace transform of and then plus all those things. And now I can write all these things one by one. I know that the Laplace transform of the unit step function is 1 over s. Okay. Then I have the Laplace transform of the unit step function shifted by an amount minus 2 in time domain. Okay. So let me refer to the time shifting property and find the result, write the result from there directly. If I shift it by 2 seconds, then I should get e to power minus 2s times the transform of the function, which is 1 over s. Then I need to write the transform of this part. So this time my f of t is t, and I shift it by 2 seconds. Okay, so I need to take write this as since the shifting is done by 2 seconds, I have another e to the power minus 2s term, and I multiply that with the transform of unit ramp function t times u of t, and I can find the transformation of this unit ramp function from the Laplace transform table. It is this function, and n is equal to 1, right? So since n is equal to 1, this is equal to 1 over s to power 2. So this is from Laplace transform table, from And this should be the same thing as this result, hopefully. Oh, this should be positive. So this was positive here. I don't know why I put minus sign here. So there should be a summation, and then there should be a plus here. And then it is the same thing as before. Okay, so I think this is a nice example showing how to use the properties to calculate the transformations. So you will most probably need to do something similar to this in the exam. I like doing things. So I give you the Laplace transform table. You will have something similar to this. Probably you will not have such an elaborate table, but at least you will have the transformation of some basic functions like the sine function and cosine and these unit step and some basic functions here. And then by using the properties, you can calculate complex functions very easily. Okay, so for example, in this table we have all these functions written as separate items. For example, this doesn't need to be here because you can calculate this very easily if you know the complex shifting property. Okay. So I think this is enough about Laplace transformation properties, and there may exist some additional properties, but these are sufficient for our purposes, and we will be using these properties. Okay. So this table summarizes how we use Laplace transformation in this course, and I think it's a really nice summary. So let's take a look at the left part of this table, and maybe I should just copy this to other file and then talk about it there. So this is what we should normally do in system analysis, right? You are given a physical system, and so we assume that it is a linear and dynamic system. I will talk about this later. We start by writing the equation for that system. Okay, so by using the laws of physics, we can write some equations that represent that system. And since this is a dynamic system, these equations will be in the form of ordinary differential equations. Okay? Then, if you want to calculate the response or the output of a system to a given input, what we need to do is we need to take this input function and then solve these differential equations to calculate the output. Okay? So here we use the classical techniques for solving differential equations. And then that gives the response in time domain. But we know that solution of differential equation in time domain is not an easy thing, especially if you have some random and complex input functions. So this part is really difficult, solving the differential equation, especially if you have high order differential equations or if you have multiple equations that are coupled together. Then the solution part is certainly a very, very complex job. Now, what we do here is, instead of trying to solve these equations, the differential equations, we take the system equations, which are differential equations, then take the Laplace transform of these equations. But remember the differentiation property, while taking the transformation, Laplace transformation, the derivative terms turn into algebraic terms of S. Okay, so when we take the Laplace transformation, we are left with some algebraic equations of S. Then we calculate, we take the transform of the input function as well, which becomes a function in S domain. Then we solve these equations for these inputs using algebraic techniques. So the solution here is a lot easier. Instead of trying to solve the differential equation in time domain, we simply solve these equations, and then we obtain the response in S domain. And then we can take the inverse transform of the response in F domain and obtain the response in time domain. So we take a longer path, but this longer path is in fact much more easier compared to the shorter path, since it doesn't involve differential equation solving. Okay, so this is what we do in system analysis, and so let me just copy this over there, and then I can add a few more things on it. So the response in time domain here, this is a function of time, y. Let's call the output of system y. And so if you go through this longer path, here you obtain the response in S domain. So you obtain a function in S domain, capital Y of S, and by taking the inverse transformation, you transform this into time domain, and you get exactly the same response. Okay, so the same response in time domain can be achieved that way. So this is how we are going to use Laplace transformation. Okay, so that involves taking transformation of some differential equations, then solving those differential equations turn into algebraic equations. Take the transformation of the inputs to the system, whatever the input is, you calculate the transformation for that, and then you solve these algebraic equations together with this input function very easily, very easily. Calculate the response in S domain, and then go back to time domain by taking the inverse Laplace transformation. Okay? So we have just 10 minutes left, and we can start talking about this tomorrow. So I don't want to go any further today. Do you have any questions? So again, I'm going to give you a homework, and that homework will involve this Laplace transformation. You will have to calculate transformation of several functions, and in some problems I will ask you to use the integral explicitly. So I will ask you to take the integral, and then I will ask you to calculate the same result by using the properties. So that will be a good exercise, and you can find similar problems online. So this file, for example, includes some examples. I can give you this, but you can find this very easily on the internet. So you can find a lot of examples like that. So probably I will take the question from such a file. So if you need some help doing the homework, I suggest that you go to Google and find some problems there, and chances are very likely that you will find the exact same problem I used in the homework, so you can just take it from there. Okay? So I'm going to see you tomorrow, hopefully. Yarın öğleden sonra tatil ya, 12.40